Welcome to episode 18, Landing the Rocket. Rockets that place satellites in orbit have at least two stages, and the goal is to soft land the large, expensive first stage so it can be reflown like an airplane. There are YouTube videos of one particular company, SpaceX, doing this. The YouTube also has animated models of whole flights with physics and running parameters from launch, through stage separation and finally the landing of stage 1. Landing the first stage is possible because it was never going very fast. Returns from orbit and moon missions have required heat shields, because speeds are in the 15,000 mile-an-hour range or more. We don't have that problem. Our first stage finished its main work after achieving around 1600 meters per second speed, 3,600 miles an hour, at more or less a 45-degree upward angle. This is where stage 2 must take over. This happens at around 60 kilometers high and 60 kilometers downrange. Once the top part of the rocket has separated, the bottom, now with 85% of its fuel gone, can be easily redirected and slowed with bursts from 3 of its 9 engines that were needed for liftoff. There are typically 2, 3-engine maneuvers at high altitude. The first is to get the first stage flying back towards the launch area. This is a 25-second backburn using a third of the remaining fuel, or 5% of the original fuel load. The second, the re-entry burn, is to slow the body from almost 1,600 meters per second to 550 meters per second. This happens between 70 kilometers high, still in space, and 21 kilometers high, up where spy planes fly. It uses 8% of the original fuel load. Now we need a miracle. We have only 2% of our fuel left. Our miracle is air resistance for slowing. From spy plane altitude to normal plane altitude, we actually lose falling speed just from air resistance. About 9 seconds after model time starts, we will light up a single rocket engine for our final deceleration to a soft landing. The model is a bit too big to go through block by block, so we will talk about the major functions and how they are connected. We have our normal acceleration, velocity, displacement chain from earlier motion problems. To make acceleration, we have to sum our 3 forces: gravity, air resistance and engine thrust. Gravity force has to involve rocket mass, which reduces. Air resistance has to involve the square of velocity. To control the engine thrust, we need a control program idea. Our instinct says that deceleration should be uniform. This gets us even strain on mechanical components. But uniform deceleration for us cannot be a single thrust setting. We have changing conditions. Rocket mass reduces while we thrust. The air we are falling through is thinner up high, thicker down low. The air may be moving, creating air pockets, which means uneven support. What do we do? For more or less uniform deceleration, we should think of steadily changing speed. What should drive our changing speed standard? Let's make it with respect to altitude. Each altitude point must have a proper speed paired with it. That way, if an air pocket knocks us off our altitude-based speed schedule, we can get back on schedule by adjusting thrust. What is the easiest way to make up a set of proper speeds from altitude? We will think this through in the forward direction, then take one step back. Deceleration is a function of time to the power of 0. Anything to the power of 0 is times 1. We see our constant acceleration number in meters per second squared times 1. Decreasing velocity is just the negative m function of time to the power of 1, which is just the negative of time. Falling displacement is a function of time to the power of 2. Lots of change of altitude per second early, much less later as we slow down. This is needed for a soft landing. So now we have to think backward. If I am generating a speed standard from altitude, at some point I have to take the square root of altitude. This happens in the speed program generation part of our model. A couple of constants help shape the response. This speed standard is compared with our present speed and an error signal is generated. The error signal is fed to a PID so our control system won't oscillate. The output of the PID eventually makes it to the account that represents thrust setting. Finally, we have a couple of events to handle. We don't want thrust between 5,000 meters and 3,000 meters high, so we need a selector for the thrust program that detects when we pass through 3,000 meters. We also need to shut down rocket thrust quickly when the landing legs touch. That is another selector. We have arranged a stress test for our control strategy. It is to see if we can get back on our deceleration schedule if we are knocked off of it. At around the 16-second point in the model, we hit an air pocket. The support of oncoming air is cut significantly for part of a second and increased for another part of a second. How will our control system handle this? It must make the right decision quickly because landing is only 14 seconds away. Let's run our model and look at graphs. Sheet 1. This is our acceleration, velocity, displacement set. There is little acceleration before around 7 seconds while the rocket floats down at terminal velocity. Likewise, not much change in velocity during this time. The bottom graph is altitude, which is decreasing steadily. We see acceleration activity and significant speed change over time after the rocket engine is started. Both altitude and speed on this scale show us landing at about 30 seconds. But was it a safe landing? We enlarge the final second of both speed and altitude to see if we touch down at a safe speed. We say that altitude is 0 at 29.9 seconds. Then we check speed at 29.9 seconds. Around 1 meter per second. The landing legs are designed to handle this impact. No damage to the rocket. To keep the model simple, we ignore any model data after 29.9. Sheet 2. The top graph is our newtons of support from air resistance. It gradually climbs during the first 7 seconds as air of greater density is encountered. Air resistance peak occurs just as the rocket engine starts. As the engine gets the speed down, air resistance falls faster from reduced speed than it might rise from entering to enter air. Our air pocket occurs at around 16 seconds. The middle graph is rocket thrust. At its beginning, it shows a bit of overshoot as the error between program speed and actual speed is quickly nulled out. Engine and air resistance share the load of maintaining the deceleration program. When air resistance drops part of the load during the first part of the air pocket, the engine must pick up that load. Sheet 2 bottom graph is loss of rocket mass as a function of time starting when the engine is started. We go from around 50,000 kilograms to around 43,000 during the burn. I hope this plucked from the headline science story was fun. Advanced strategies for soft landings are essential for going to the Moon, Mars, and for getting to asteroids so we can mine exotic materials and build better rockets to go farther. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.